probably saw me working in the last weeks for quite a long time, and as I leave in already 2 days, I want to present you today my whole project from the beginning to the end. So, first of all, I will explain you the whole process, what we did from the beginning to the end. Then I'm going to discuss with you the water analysis results. I will present you the concept and how I made it. Then you will see how we implemented the filter, like how we constructed it. And I will inform you about some challenges that we had, but most importantly, the benefits that my project will have for Hitas. So here you can see the whole procedure. When I arrived, we first had to make a water analysis. That was the most important thing, to see which things are problems in the water, what we have to eliminate. So first of all, we took the water analysis. This took quite a lot of time because the borehole wasn't completely ready. The pump was not working, but we could fix it quite fast. And then we asked for an offer at Louis Pasteur's side, the laboratory. We got an offer and they came to get the analysis. After 1 week we had the results and could finally start with the whole concept making. First of all, when we received the water analysis results, we had to check which are the problems, which values are not in the limits of the drinking water. So after we identified the problems, we could start with the concept making. First of all, we plan to do it with a company named Autocon that is located in Germany, and they have a very innovative technology to disinfect the water. And 1 year ago, when Emily, the other German student, were here to plan everything, we were in contact with the company, but now it turned out that their offer was just not in our budget limits, and it was very, it was just malcommunication, because 1 year ago the offer was quite good, but now they raised it too high so that we couldn't implement it. That's why with my professor we planned a concept without Autocon, just by ourselves. And it took a few weeks until we had it finished with all the details, but then we could finally start the material procurement. So we checked in the environment where are the materials available, we got a driver, and we got every material at Hitas to finally start building it. And then we constructed the filter in quite a fast time. It was like 1 week to present it on the open door day. And there we already had a successful presentation of the filter where guests could see it. But after that we still had to improve a lot, because one filter was leaking and we had to seal the leak before using it for the building. So that's what we did the last weeks. And now tomorrow we will bring the water to the laboratory again. I'm afraid we couldn't do it in the time that I was here, so we will get the results next week. But it will be no problem, we can prepare everything. We can already use the water for washing, because the water that we use right now is not the best quality, so our filtered water has already a better quality than that. And it's just, we need the test result. So you will see the results next week. But let's just check the results from the first analysis that I took at the beginning. You can see the only limits that are exceeded are the bacteria, the germs, and the bacteria. So we identified the problems. There's a germ contamination and a bacteria contamination in the water. Then we analyzed with the microbiological analysis. Second analysis we did was the physical-chemical analysis, and here you can see that the water had a color that is because of all the particles, mainly iron. Iron, you can also see here, that is way too high and over the limit of 0.2. Another problem was the pH. It was a little bit too low, and we had to rise it a little bit. Furthermore, there was ammonium in the water, which is probably because a little bit of wastewater enters underground in the groundwater, so we had to find a way to filter it out. To make the concept, we had a few options for the different problems. So let me start with the pH. If you want to raise the pH, you can use two methods, aeration, but aeration is very limited. You can only use aeration for under 0.5, an increase of under 0.5. So we needed we needed to raise it from 6 to 7. So we needed a method that can raise more than 0.5. So we had to use the minerals. Then you can choose between limestone and dolomite. They both work the same way and raise the water through a chemical reaction. For iron, there is the method of oxidation, and you can use 3 different methods. Also aeration, because as soon as water gets in contact with air, the iron dissolves and undissolves and precipitates. Another method is chlorine. It works the same way. As soon as water gets in contact with chlorine, it precipitates, the iron precipitates, and you can also use other chemicals for it. For ammonium, there are a lot of methods that are normally used for wastewater treatment, because wastewater includes a lot of ammonium, and we need nitrification for it. To do it, we have all these opportunities. I'm not going to present them all because they all have a different procedure and it's not too important right now. And for the particles, we just needed filtration, for example with sand or a microsieve, to hold back all the particles. At the end, the bacteria and the germs, you have to disinfect the water. You can do it via chlorine, UV disinfection, or with a slow sand filter that removes the biofilm and disinfects the bacteria. So our aim was to get a really natural, easy and chemical-free process without a lot of maintenance. That was our goal. So let me show you which discipline we take. For the pH, we took limestone because it has no limit to rise the pH and it was locally available. For the iron, we used aeration because it's chemical-free and you just need to let air come to the water, which is quite easy to realize. For the nitrification, we chose the drinking filter because it's very often used for ammonium, and you can choose which size you want. It's easy to adjust to your filter project. For the particles, we choose the sand filter because it's just very easy to implement. You get sand everywhere, and you just have to maintenance a little bit every few weeks, which is not too much. For the bacteria and germs, we decided to use the UV lamp, as chlorine is often used, but you always have to buy new chlorine. So that are running costs that we didn't want, and a UV lamp just disinfects it in a very short time, and all the time. You just have to change the lamp about every year, which is very easy to realize. So now you see which discipline to choose for the concept, and let me give you just a quick overview how my filter looks like. We start here with a borehole and a pump. After that it goes in a reservoir to store the water. The throttle valve reduces the speed. It gets into, I'm just doing very quick because I go into detail. We go to the limestone filter, then in the aeration filter where the iron oxidates, then into the treating filter with the charcoal, in the sand filter, in the intermediate tank to store the water until it's pumped upwards through the UV disinfection to the storage on the roof. Now I explain you the steps in a little bit more detail. The borehole has a deep of 73 meters. It's outside in front of the building. And the pump that we use pumps about 80 liters per minute, so it's quite a strong pump. As it is such a strong pump, we just pump every 20 minutes for 1 minute 80 liters into the first tank, and then I will show you why. Here you just can see how it looks in real life. Here is the opening of the deep borehole, and that is the electrical device to control the time of the pump, when it works, when it starts working and when it stops. So here you can see the pre-reservoir. As I told you, every 20 minutes we pump for 1 minute 80 liters water into the pre-reservoir, and then the throttle valve reduces the speed so that the outgoing flow is just 4 liters per minute for 20 minutes. That's because the water needs to rise, but needs to go through the filter at a specific speed. Then we can do with the throttle valve, and yeah, if there is a malfunction with the pump or with the timer, we just have an emergency drain where all the water goes out so that it doesn't flood the first floor. As this tank is situated in the first floor. So let me show you how it looks in real life. Here is the tank, here all the water enters through the pump, and here the emergency drain is. If it raises this level, it just flows out, and here it normally flows out to the next filter. Okay, let's continue with the limestone filter. That comes after the pre-reservoir. It just filled with coarse limestone. It has a volume of about 250 liters, and it has to be closed. Because if it would already be open, some of the iron would already precipitate and pollute the filter. That's why we keep it closed until the next step. But first of all, the water comes here from the reservoir and enters here. It's spread by a bucket that is just on the side, so that the water spreads through. Then, when the pump works, it just rises slowly until it reaches here, the level. Here it flows out to the next filter. And if we have to wash the filter, we just have a valve down here, which we can open to let all the water out, clean it a little bit, flush it with water, and let it out. Okay, so next slide, you can see how this filter looks in real life. Here the water comes in, the valve to clean it, and upstairs the water goes out to the next filter. The next filter you can see here. That was the most problematic one because we had to glue some containers together, and we finally did it, and it concludes a volume of about 250 liters, and it concludes an aquarium pump that pumps air with these diffusers. So up there's a aquarium pump, and it pumps air, so here the air diffuses and it's spread in the water. The water enters up there and it goes down until here, gets in contact with all the air, and then it goes up through this pipe in the next filter. And here, so when the iron gets in contact with the air, it already starts to precipitate. It will go down here, and if there is too much collected down here, we can just open the valve and let the water with the much iron out. But not all the iron settles down in that short time, so the rest goes up with the water through the pipe in the next filter and is filtered out later. Here you can see how it looks in real life. The water enters up with a shower head, and it goes down in the pipe. Here you can't see very well for this sand filter. It has a volume of about 220 liters and it's filled here. This is a layer of gravel. Then we have a layer until here with coarse sand, and then on top a layer with very fine sand to filter out even very small particles. It's just mainly for the unresolved iron that is stopped here in this filter, but also other particles that might be in the water are filtered out. This is how it looks in real life. The water enters on top and drops in the filter. It just raises down and is going here to the next filter step. That is already the intermediate tank, which is placed in the basement. So when the water rises down, it's stored here. It raises through the incoming water, and when it's reached a certain level, the pump starts to pump the water upwards. But for the next process, we need also a specific speed, which is why we have this water valve to control the flow. Here's how it looks in real life. This is the intermediate tank in the basement, and upstairs there is a pump with the control of the pump. So now we come to the UV disinfection. It's just a small lamp, and the water can just enter through the lamp. We need a flow rate of 7 liters per minute. You can choose a bigger UV disinfection lamp, but the price rises a lot with a bigger lamp. And we calculated the need for this building of water so that we could choose this specific lamp. And it just, when the water enters here, it just flows through the UV lamp, and the UV light kills directly all the bacteria and the germs just in a few seconds. So that when it rises to the storage on the rooftop, it's completely bacteria free. Here you can see in real life, this is the UV lamp, and if there's a problem with the UV lamp, you can switch the valves and let it flow here to fix the problem. Okay, so the last step is the storage on the rooftop. It already exists. It's at a height of 24 meters above the building. It has a capacity of 10 cubic meters, and so the pump pumps all the water upwards, and here is stored until you use it in the building for everyday shower or water consumption. And as our project has to work 24/7. So right now, it's just if you use water, the pump downstairs detects this and pumps new water. But we need a continuous speed for our project, so it works 24/7. So if the storage will be full, we just install an automatic valve downstairs in the basement. So if the storage tank is already full, the valve opens and the water is discharged before entering the storage to not affect the overflow. So let me go on with the implementation of the water filter. Here you can really quickly see a material list. You don't have to go through everything. Just as an overview, we needed all the reservoirs, we needed glue for the reservoirs, we needed a lot of plumbing materials, and also the technical devices like the pump, the UV lamp, or other materials. On the next slide, you can also continue with the material list. Thank you. Here you can see just the last material that we also had to buy. And on the next slide, you can see the tools that we needed to implement this filter. So most of the technicians have all these materials, so it's quite easy also for other households or companies to build this kind of filter because you don't need very difficult tools. Let me continue with the finances. Our aim was to stay under $1 million. It was also our first project in this dimension, so we had to view with the process
things, so we are quite happy. You can see where it's used for, just an overview, and you can see that the technical devices are, of course, the most expensive things, the pump, the UV lamp, and also the screwer. So that was the most expensive ones, but it will stay for a long time, so the cost definitely pay out. So now I prepared a video to show you the whole implementation, a few steps, and cut it to a whole video. And yeah, just to give you a view about our whole work with Carlos,